Oh, jam started.
He just wants to
Oh,
be involved.
hello.
He
What
is
do you
also
want?
interested in women who changed history.
He's um he's having a big long drink. He is very funny. He has his favourite water bottle, so we have a water bottle on each level, and he only drinks from one of them. So
Oh,
you
so what if he's
try.
upstairs? He like comes down.
Yeah. He has his favourite water bottle. That's his water bowl. That's the one he wants, and that's what he's come for. Yes, I'm talking.
That's cute. And then you have to wash and keep the other ones topped up
Of
just
course,
because.
because you feel a bad human if you don't.
We have a cat fountain that's exactly the same. We like change the filter. I'm sure I've told you about this before.
Mm-hmm.
She never ever drinks from it. She drinks Ted's disgusting water bowl.
It's mad, 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 mad. Would you like to hear a story?
I sure would.
Um, Great, because I've got one. So the got a little intro. Think your local pharmacy supply chain starts with a corporate lab. Think again. It actually began with an 8-year-old girl mixing chemicals in an attic, growing sapphire blue crystals, and learning to spot patterns that. Oh, hang on, I haven't. Okay, I'll start again. Think your local pharmacy supply chain starts with a corporate lab. Think again. It actually began with an 8-year-old girl mixing chemicals in an attic, growing sapphire blue crystals, and learning to spot patterns that standard science deemed impossible. Fleming got the credit for penicillin, but today we meet the lady who gave it to the world. Today, we dive into a story of secret structures and medical marvels, all achieved with a hidden disability. This is the story of Dorothy Hodgkin.
Ooh,
I
like a
know.
scientist.
It's a
Very cool.
really, really good story, I think, as well. And I hadn't heard of this lady like many of the people that we do. But if you want like a proper version of this story, there's a really good In Our Time Radio 4 program on Dorothy, which I've used for some of this. I've also used a few little blogs, the Royal Society, the Nobel Peace Prize Society's in there, Britannica, of course, Bristol Uni, and a whole little sprinkle of sources to bring you the story of Dorothy. So Dorothy was born in 1910. She was actually born Dorothy Crowfoot.
Oh, that
um,
sounds like Native American name.
Oh,
That's
does it?
interesting.
So she
Yeah.
was actually born in Cairo. Her parents worked in North Africa and the Middle East in like colonial administration, so they were quite high up in that. And then later they moved into archaeology. I think this is a very my generation reference, but there was this TV show called The Wild Thornberrys, and it was like this
Yeah.
cartoon. Yeah, do
I'm
you
too
know?
old. Nope.
Sure. And it reminds me so much of that show, her upbringing. It's hilarious. Um, so she was the eldest of four girls, but she was very much left to her own devices. They really encouraged her to be very self sufficient. And because they were kind of in all these amazing countries and cultures. Her education was a little different. So her mum taught her a lot. Her father actually worked for the Ministry of Education, but in terms of like their culture and how they grew up in their home environment, it was all about being peaceful, being open, being allowed to explore. So she had actually quite a lot of freedom. They also encouraged her so much. So they encouraged her to study plants, natural history, flowers, drawings. And she did have like this roaming kind of childhood where she was just allowed to go out and be wild and free. And I think that's probably because she was in Cairo. So they used to spend the winters in Cairo and the summers in England. So they kind of alternated.
Just sounding idyllic as a childhood.
Yeah, minus the colonialism. Sounds great.
Yeah,
So,
that part's a little bit tricky, but as a childhood, that sounds terrific. Like, go
really
look at some
cute.
plants.
Um, so yeah, she didn't have this necessarily formal structure, and But it was actually this childhood that led her into science in a different way. So, like I said, her father became an archaeologist. He was really into mosaics. And what they did was they would take her on digs. So she would go digging with her father. And on one of these digs, they found this amazing mosaic floor. Like digging down, and it was really well preserved. But what she had to do was dig and find these tiles and then kind of resemble the pattern. So she kind of built this power for power recognition, because obviously when it's a burial, it's all broken tiles, it's all a mess, and she actually figured it out. She used her instincts to figure that out and tried to draw and record them so that she could, that was her contribution to the dig and to the research. Those drawings still exist today, and obviously digging in those conditions, it's quite painstaking work, as is the power of a child to record and draw and document that correctly. It's quite a lot, isn't it? It's quite a big thing.
It sounds like she did a great job, but I'm thinking that originally it was just her parents going, "Oh God, the child is with us. We need to get something to keep her
most likely
occupied and getting into trouble." So then they were like, "Oh, this is actually really useful."
Yeah, and she had little blips like this throughout her childhood that actually contributed to her future in science. So that is one where they were like, just go and play and dig. And then the other one was that her uncle Joseph actually gave her a chemistry lab set when she was about 8 or 9, and she set it up in her attic. And this is not one of those cutesy leapfrog kind of chemistry sets. This is like the proper deal. Like, it was a proper chemistry set he gave her with proper chemicals. So she's like 8 or 9, right, when this is happening. I can't hear you. Sorry.
Oh no, oh no. Sorry, I was just saying it sounds delightfully dangerous. That's a time gone by.
100% health and safety nightmare, absolutely. And then what also made it a nightmare was that she would go to her local chemist and get more chemicals. Just
Lovely.
That's totally fine.
Here you go.
So she gathered things like soils from the garden and things like that, and performed analysis using these chemistry sets. When she was in England, she would go to primary school. Obviously, her father's education background, he felt it was important to do that. So she was exposed to chemistry there too. One of the things that was part of the curriculum she was part of, which was the Parents' National Educational Union curriculum, which was when the idea that governesses were taught to teach, basically. One of those terms, they did crystal growing. And the way they did that was through copper sulfate. And then what they would do is they would make a solution with the copper sulfate, whiz it up in a beaker, and then they would let it dry out. And actually what it does is create these really so vivid, like I can't explain how bright blue these crystals are. Absolutely stunning.
It's beautiful. That's the color of your dress. Did you coordinate?
A little bit. I must have subconsciously loved that. That was again one of those, like I said, these little blips in history that she in her childhood that absolutely, I guess they were informed experiences. And she talks about this one in particular with the copper sulfate here, if you want to read.
Her interest in chemistry started when she was only about the age of 10, when she went into a little tiny primary school where they grew crystals, and she said herself, "I was captured for life by chemistry and by crystals."
What a cute quote. I was captured for life. That sounds
and so young to be doing like hands-on science.
Some people get that though, don't they? They get like an opportunity when they're so young, and it just informs their life path. Like, it's just very, very sweet when that happens. So I remember this is like early 1900s, so we're like 1920s at this point. It's still new, I guess, for girls to like science and being part of that world. So in secondary school, she went to comprehensive. It was mixed. It was very much the norm that boys did chemistry and girls did needlework. And she didn't like that. She didn't like that at all, because she really liked what she did with her father and at primary school and all that kind of thing. So she got her little buddy called Nora, and they kind of put their foot down and they were like, no, I really want to do, let me do chemistry. They were eventually allowed. Apparently it really helped. Well, apparently their teacher was a woman, so she couldn't really, there was no leg to stand on there, was there really? But really interestingly is that she didn't do academically well in sciences. It wasn't her strongest subject at school at all, but she persisted, she tried as hard as she could, and because of her love for it, really. The next part of her educational journey was essentially going to Oxford. She wanted to study science, and not many places did that. Oxford is one of them, but the problem was, because she was at this like state school, they weren't used to prepping people for places like Oxford, really top tier places. So they didn't know that to get into Oxford you would need 2 sciences. I think you also needed mathematics and Latin to even,
oh my god,
like be approached or get into Oxford, like even to be in its realm. So she was 16 when they figured this out, so she had time to prep that. So she continued to study even in that time when people were going off and doing different things. Her parents got her one-to-one tuition. Like I say, her parents sound so supportive all the way through this, really encouraging, open to growth, freedom, all that kind of stuff.
That's so cool. But I mean, like, how much work to do, you know, all those extra, like, I need to learn Latin in the next year and a half.
Off you go. She chose botany as her second science, which was quite nice. And it worked. She got in. She
good for her.
Yeah, which is no easy thing at all, especially at that time. And she was only, so at that time women were capped at these kind of universities. We've spoken about this in a few episodes, where like women were just not welcome in those
like places. A quota type situation.
Yeah, it was 1 in 4 basically. Every 1 in 4 students were allowed to be female. But during this extra year, what she found was, because she was very into studying into academia, she found a lecture which introduced her to something called X-ray crystallography. And it was by this guy called Bragg and his son, who had actually won a Nobel Prize for this technique. And what that does is it essentially allows you to see where the atoms are in a molecule and how they're arranged. So a pretty pattern of molecules. And she saw this lecture, was really interested, and she was like, that's what I want to do. I just want to go and do that. So she had a very clear path of what she was excited for, which was good. Even when she got into Oxford, like I said, it was capped, and there was a lot of prejudice around Oxford. She wasn't allowed in practical classes sometimes, like women in the lab is unsightly, it's not meant to be. And she was but she did, I'm screwing that up. She learned, she got into it, but she had to fight her way. It was just an extra hurdle for her when there really didn't need to be one.
Like it wasn't given to her on a plate. She had to fight for it.
Which is so dumb, isn't it? Like,
ridiculous.
The energy. It turns out she was really good at it, and she got her first in chemistry at Oxford, and she was only the 3rd woman to do so.
My God, with the extra challenges as well.
I know.
So, yeah.
Very cool. So we've whizzed along the timeline. We're now in 1932. She makes the move from Oxford to Cambridge. Shock horror. Because she gets offered a research position by a chap called John Desmond Burnell, and he is like a really important figure throughout her life story. It's kind of like her first like big girl job, if you like, and she begins studying for a PhD at Newnham College, Cambridge.
Okay.
Yeah, not our Newnham, not the Newman over the road. So this is the first time in all of her stuff where she's not been like the outsider. It's the first time where she's been with people who like what she likes. And because PhDs are so specialized, and this area, this crystallography, is quite a new area of science at the time. So it is, because of that, it's more open to things and open to different people than a traditional, I guess, set of science. And so there is this thought that it was more open to women because of that. We're going to go a little sciencey, Cara. I hope you got your science head on.
Okay.
I'm going to botch some stuff. You're going to botch some stuff. We're just going to try our best as we go through. But what I've got here is a little definition on what crystallography actually is.
Okay, so crystallography, a branch of science that deals with discerning the arrangement and bonding of atoms in crystalline solids and with the geometric structure of crystal lattices. Of all the words to fluff, I've used the word structure before in a non-scientific way, so, but there we have it.
Yeah, so basically making these pretty, I keep saying pretty, like I'm feminizing it, but like these structures of atoms.
Pleasing, geometrically pleasing structures. And I get it, because she's a curious cat. She's been raised to go out and look into things and suss stuff out. So she's now able to look deep inside to the most basic level of thing. I can see why this was for her.
Yeah. And it's not just, it is for her, but she's doing it at the top level. Like, this is like the most prestigious place that you could be studying, the most innovative, I guess it's like, I'm trying to think what today would be. Really depressingly, it's probably AI, like something like that, when you're on the cutting edge of something. She was definitely at that. And on top of that, we know she's determined. We know through all this education that she's been doing, through like a genuine love and interest of it, like she said. She's working with the top in the field, who is this guy called Bernal. He has actually developed a photographic technique which sped up a lot of this research and a lot of this processing. So when you're looking at atoms and trying to work out the arrangements, photographing them actually makes things a hell of a lot easier. And he'd actually found a way. Yeah, he'd found a way to, because obviously we're talking minuscule, really, we're talking so tiny. He'd worked out a way to photograph them. And that leads us on to what is called X-ray crystallography. There's a little quote there explaining that a bit more.
Modern crystallography is largely based on the analysis of X-ray diffraction by crystals acting as optical gratings. Using X-ray crystallography, chemists are able to determine the internal structures and bonding arrangements of minerals and molecules, including the structures of large, complex molecules such as proteins and DNA.
It's pretty cool stuff, right?
Yeah.
It's pretty exciting, and but also not easy. So the way they did it, and this is where I'm going to botch it up, because I listened to In Our Time twice and I read about it, and I think I got more confused than I did. But basically, lights with a really high frequency shine through these crystals, which are obviously very, very tiny. We're talking molecules, we're talking minerals, we're talking small. Because of the X-ray light and because of the light frequency, you can see all these different atoms. And if there's an atom, it will show a black spot, and that black spot will go on the photographic plate. But the problem is you have hundreds of these black spots in a really, really tiny space on the photograph. And it all depends on the angle you take the crystal, because then if you take another photo at a slightly different angle, you're taking a picture of the same spots, but it will look slightly different. So it is painstaking stuff trying to work out these spots and comparing them at different angles, so you get, because obviously it's 3D, it's not 2D. So then you have to do tons of maths to work out the angles of the original spots versus the second spots, so you can actually build a 3D structure. So this needs tons of maths and algorithms and things. You need to be able to detect patterns as well, just like we were saying earlier. There's definitely themes throughout this. And also it's physically tough, because you're having to keep the crystal wet enough so it doesn't dry out and change the structure. You need them as stable as possible for a scientific experiment. And, it's quite eye straining technology. Eye straining, it's very manual, there's no computers, you're having to write all this mathematics out by hand, there's nothing you can do. Yeah, we're in 1920s. But that's what she did. And when I say there's hundreds of these dots, yeah, that's absolutely true. There's hundreds and hundreds. So she needed a way to categorize them. So the way that she did that, all through just plain eye, by the way, was she'd create a scale of 1 to 10 of how big the dots were, and she would assign a scale of 1 to 10 to each of these dots to show their intensity. And then she would write the numbers against a label, and there's 100 of these. She would arrange this data into columns for every type of spot there were. She would total the columns up. So it felt to me very Enigma, like very Alan Turing.
Just working on some other level.
And then she'd have this, and then she'd have to work backwards to build it into the structure of a crystal. That is a very, very botched explanation of what she was doing. But I think the things I want to get across were it is painstaking, it is manual, and it is big, big, big data that we're working with,
manually doing that level of data crunching.
These tiny dots, tiny little...
It's just
tiny
boggles the mind.
Hundreds of them, yeah. And Dorothy, this was much later in her career, she gives this quote of her time there and actually what this task was like.
Dorothy later remarked, "I should not like to leave an impression that all structural problems can be settled by X-ray analysis, or that all crystal structures are easy to solve. I seem to have spent much more of my life not solving structures than solving them." Oh.
Which, fair, absolutely fair.
Yeah.
I think that also shows how long that process takes as well. Like, you'd think, oh, dot 1, dot 2, I just write 100 numbers down. No, it is so much like the fact that she had more fails than successes just show how difficult that was, right?
I also love the use of the word solving. Like, she sees it as a puzzle, a problem to solve, and something to unravel.
That's a cute little pickup. Yeah, absolutely. So like I said, manual, painful, and it actually contributed to her arthritis that she had while doing this. I think she might have developed arthritis in a pregnancy. I think I read that in the research somewhere. But either way, she was doing a lot of this work with arthritis. Her PhD was awarded in 1937 for research of X-ray crystallography, which we know what that is now. So she's kind of got this down. Then the next thing, because you've got these crystals, you can expand that into looking at proteins. Proteins are everywhere. One of the, I can't remember if it was the podcast or something I was researching, described them as the workhorse of biology. They build absolutely everything. They are the base of everything they do, so much. But and also they contain thousands of atoms, which is what she was plotting.
That's right in her wheelhouse then.
Yeah, it is. And it's a much bigger project. So she's like, let's take this thing and let's just expand it like tenfold. So the way to study, look at me talking about it like I know about it, but the way to study proteins essentially would be to purify them, so get it in its absolute purest form first before you then start photographing it, x-raying it, all that kind of stuff. So that actually takes a while in itself. She did manage to achieve that, so that's an achievement in itself, drilling that down. And her and Bernal, her mentor, actually took the first ever photograph of a protein. So they did achieve that by distilling it down and down and down and purifying it, which is absolutely hilarious if you think about the amount of photos we take on a day-by-day basis.
Yeah.
So even though that photo wouldn't lead them to the structure necessarily, it was deemed the dawn of protein crystallography, which is like a whole nother, like you said, a whole nother subset, I guess, of science that they were just exploring, just starting to like peek into. And also, what a world that we have the phrase the dawn of protein crystallography.
Science is wild.
Science is wild. So in 1933, Dorothy was awarded a research fellowship. So not studying, actually being paid to do it.
Oh, paid
which
work.
is very
Nice.
very
After
cool.
all that, oh my God.
Yeah, and it's actually a really cushy job. Like, they really made a point of this in the research that, first off, it was at an all-female college in Oxford. So this is at Somerville College in Oxford in 1933 to 34. It was a really supportive working environment. They supported her. She actually got paid maternity leave through this. Paid.
Nice.
Yeah, so the fact to get maternity leave at that time was hard enough anyway. To get it paid, it means you're so valued there. Absolutely. It was absolutely incredible for the time. She started to teach chemistry using her own lab equipment. She had access to the best lab equipment. And the college appointed her its first fellow and tutor in chemistry in 1936.
Oh, how cool.
It is very cool. And I think another thing is this is her loyalty. So she stayed in that post until 1977.
Wow.
Yeah, I think she knew how special it was, which is very sweet. So around this time, she was given crystals of insulin to photograph. And we know from our protein little discussion there how hard it is to photograph a protein. Insulin was very much the same. It took a whole year to photograph properly the insulin so it showed the structure. And when she did, and then had a paper on it to back it up, that was like, she was seen as like the top dog in her field. It was like epitome of, crystallography. And she's just in her 20s at this point, but she really has cemented herself as such an expert in the field, which is absolutely mad. So that's insulin, 1934. And so after this, we talk about a different molecule, which is penicillin. Penicillin is very unstable and very hard to isolate. And let me start that again. Penicillin, you'd often think is a tree. When you think penicillin, you think of
Like, it's a mold, isn't it? Like a spore?
Yeah. And not great and quite dangerous. It was discovered by Alexander Fleming in 1928, and there's that famous story of he just left something to mold on the side, and basically he discovered it, but then he deemed it too unstable to do anything with, and just kind of let it be, just let it go. So he just left it. 10 years later, after he discovered it, Oxford started to research it, and they wanted to establish how well it worked. So they did animal testing. So they gave 4 mice an infection. 4 of them had penicillin, 4 of them didn't. Those with penicillin survived the infection. Just have to wait for Joe.
He does not like mice getting penicillin, obviously. It's like, no. Or maybe he wanted all the mice to get the penicillin.
Okay, I think we're back. Yes. So they knew it was good. They knew, okay, these mice have survived. Maybe it's useful. So, and at this time we're hurtling towards the Second World War, right? So they were like, okay, so if it saved those mice, maybe it can save other people. So Allied governments recognised the potential of this potential drug, and the race was on to convert it into a mass-produced drug. So
it's unstable but effective. So we have a bit of a problem.
Yeah. Who do you call? You call the best people in the field, including Dorothy. What they found, that because she couldn't test it because it was unstable, but what she found was that actually the breakdown of its products, and and this is some science, the sodium salt of benzyl penicillin, which is called penicillin 2, could crystallize because that was stable. All right. So she drilled it down as much as possible. She worked on this with a lady called Barbara Lowe, and were given such a tiny sample, and to the point where she actually wrote to her husband, I've spent my whole day looking at microscope teasing things with a pin, which again, if you've got arthritis, it's not easy.
Oh, yeah.
And so they're working with this byproduct of this tiny sample. And they actually had to use a slightly different technique to be able to crystallize it and confirm its structure. And that was something called the heavy atom technique, which is the idea is that you add in a really heavy atom into the molecule, so she could determine the different phases of the X-ray, allowing her to see the exact arrangement of atoms. So basically she introduced something else for it, and then that, because she knew what she was adding, she then could take that away from her calculations and everything and be left with a structure of the breakdown product of the penicillin. So can you see how many layers?
My God, how clever. Yeah.
It's
oh my
mad.
God.
It's absolutely wild. And to help her with this, she did gain some access to computing facilities at the time. So again, think Turing, think cards, think the clocking thing with the spaceship thing.
Chunk, like things turning in gears and steam.
Absolutely, not tappy. So this did speed up some of her calculations, and so what she did with all this heavy atom technique and breaking it down, the byproducts and stuff like that, she got a 2D structure, and then this machine allowed her to pursue a 3D structure of penicillin, and then because they'd worked out how penicillin is built, they could then replicate it, which is very exciting.
That's amazing.
It's absolutely insane.
The fact that a computer that manual and kind of beginner, like the beginning of the computing era, was able to accurately 3D model something from a 2D image.
It gave her the calculations to be able to do that. So she did it. She was the one who built it, but it gave her the base, it sped up her calculations, basically.
Oh, I see what you're saying. Okay, so she's
it's not like 3D
doing the hard work, right?
Oh my God, yeah.
Just spit out a penicillin tablet.
But it just shows how not reliant we are on technology today, but how used we are to technology doing this really cool stuff that you assume, oh, it did that, but actually no, like humans would
a person did that.
Yeah, like it's mad. And no wonder things took so long. So she did it. She cracked this penicillin thing, and she is the reason we have penicillin today available in a stable form that we can use.
That literally, so I mean, cool. the number of lives that were saved, including probably us, my son, everyone has had, like Charlie had scarlet fever as a child, which was often fatal in my parents' generation. That this is why it isn't anymore.
Yeah, because this lady worked out how to stabilize penicillin, which is so cool. She wasn't allowed to talk about it because it was the war and for security reasons and things like that. Findings and things were not made commercialized. You know what I mean? It wasn't out there for the big drug companies to use until 1949. Her 3D molecular structure of penicillin is available to see today. It's in the Science Museums Group's collection. There's a really cute picture of it there.
It's attractive as well. I know that's not the point, but I'm just saying it looks like a sort of like post-war sculpture. It's lovely.
Yeah. And yeah, exactly. And to me, it looks like a child's toy, which just shows how simple my mind is. I'm like, oh, that's cute. A kid could play with that. No, Vicky, it's like a groundbreaking science. So this is kind of in the 40s, right? Late 30s, early 40s. At the same time, Dorothy took part in meetings which led to the foundation of the International Union of Crystallography. So like I said, this is a new realm of science, and she was like taking it to a global stage, basically. She wanted an actual scientific community based around this and helped create one. She was elected Fellow of the Royal Society as well in 1947. So, like I said, she's so important in that field and she's so well respected in that field.
This is bringing me back to the lady who invented the standard for plugs and
Yes,
her name
Caroline
was just,
Hassett.
thank you.
Yes.
The fact that she's in a groundbreaking field seems to give some latitude, you know, that people are prepared to accept her as a player in this space. And then, you know, setting up these foundations, there's a lot of parallels.
And like at the same time, actually, as well. So same time frame and not a million miles away. So
Yeah.
Dorothy's in Cambridge and Caroline was in London. So it just shows.
I think they'd have been friends. They'd have
loved each other. Yes, absolutely. So penicillin, like we said, big hitter, big thing.
Yeah,
important.
I'm a big fan.
Would you like another big hitter?
Yeah, go on.
Let's talk about B12. So I've had B12 injections. You held my hand at my first B12 injections. And we kind of use B12 today. It's kind of seen as a well-being thing a little bit, isn't it? It's to make you feel brighter, happier, better. But back in the 1920s, it was known that a deficiency of vitamin B12 was actually led to things including anemia. Again, it couldn't be looked at fully because you couldn't isolate B12 fully into a pure compound, so it couldn't be looked at. So again, they call in Dorothy and they're like, right, we're going to give you some chemicals. Going to have a look at these crystals for me and see what you can do. And what she learned was that the B12 crystals that she was given contained cobalt, which was another useful heavy atom, which is what we spoke about earlier, the heavy atom technique. So she started on doing her investigating, doing her maths, doing her painstaking work with pins. And she was like, right, I'll give it a go. What she found was that this structure of molecule, its size and complexity had never been attempted on that scale before. So it was the biggest type of molecule in this structure to be looked at before, which meant it was a really big, complex task. We already know it's complex, but this is like the next level up. So, like I said, really complex, lots of things still being developed. So she carried on with it, and she eventually mapped 181 different atoms.
Oh my God.
I know, which is mad, to basically work out how B12 is structured.
That is such deep work. And what I can't get my head around is how hands-on and manual this process was. It wasn't just thought work. It was physical work with, rheumatoid arthritis. That is
on top of everything. Yeah,
and children. She had children.
She had 3, which is a lot of children. My
God, so she's a busy bee.
Yeah, and but it's very much passion, isn't it? A pursuit of passion. Because this molecule structure was so big and complex, it wasn't just her working on this. So there was many individuals and several institutions that contributed to this. But she was acknowledged as the driving force. So the one who was leading that project. Apart from some really snooty people at the University of Cambridge didn't agree with that. But like 90% of them did.
Yeah, who cares about those guys?
Who cares about that? We don't care about that.
Idiots.
Her Oxford lab also became at this time a finishing school for promising young crystallographers. So she, again, this thing rumbling in the background of just wanting to stretch and wanting to take this to the masses in a way, like to share it.
And to lift other people up, to bring other people along.
And which is really sweet. It's just a very wholesome story. She was also awarded the Order of Merit, and only the second woman to be honoured the Order of Merit after Florence Nightingale. So she was being recognised throughout. She was also the first woman to be awarded the Royal Society's Copley Medal, which is its oldest and most prestigious award. So people are very much... because she is making life-changing discoveries by drilling these molecules down into and working out the structure so they can be manufactured and commercialized. It's pretty amazing, to be honest.
It's lovely to see her getting the credit as well. It's not one of those stories where she's working away in a back room and some creepy guy goes, yeah, I thought of that. Like, she is stepping up and being recognized. Amazing.
And not just recognized with a Nobel Peace Prize. Nobel Prize of Science, not Peace Prize. And she was awarded that for chemistry in 1964, and that was for her work establishing structures of B12 and penicillin. So those two ones that we spoke about earlier. So I don't know if you remember earlier, I gave you a paragraph, a very quick little snippet of she managed to take the first photo of insulin. That was back in 1934. So it took a year to photograph, and then basically penicillin kind of came knocking. It was like, actually, I could save people. Why are you bothering? I've got a war to win. Yeah, she's like, I've got things to do. So what happened was that she was working on that in the background throughout her career, basically. So from 1934 all the way up to 1969. At this point, Dorothy was in her late 50s, and she managed to actually work out insulin. She managed to actually do the same thing to insulin that she had done to vitamin B12 and penicillin. It was so complex, and so that's the reason it took so long. It's because it was so much harder. Like, yes, there was these competing priorities, but also it was really, really difficult to do. They actually had a break, because you remember earlier where she's like, actually, I have more fails than wins. Like, actually, it's a puzzle, and it takes ages to finish and complete. And I imagine in that, if you have a breakthrough, that feeling and that energy must be so good. And that's just that excitement. And that's exactly what happened on the final leg of discovering how insulin is made up. There was an exciting 3-day marathon in which Dorothy and 2 of her team finished the model. So they'd like figured it out, and they just racing to get it done. She was so tired at this point. She had concentration lapsing. Her ankles were swelling because she'd been so on her feet so much. She was forced to wear slippers while at work just to like release that pressure. But she finally managed to complete her work of mapping the insulin structure in 3D, and it contained 788 atoms.
Oh, wow. So like 7 times more complex than penicillin, was it?
Yes,
or B12,
basically.
actually. That's wow. To
So
stick
no
with
wonder
it
was hard.
that
I
long.
know. I have not the patience. You know, we've been sharing like connections and stuff in our chat and Wordle, and some people say, oh yeah, I've been looking at it for half an hour. I'm like, no, I do not have this patience. I'm like, this is a 5-minute job in my world. Absolutely. So obviously she was very, very proud of this, and to have this win from starting it, like it was the first thing she started pretty much all the way up to in her 50s. That was such an amazing arc. Oh, there's a little quote here about how it's built up, but I'm not sure. Basically, she was saying it contained zinc in the middle of the molecule. But probably more exciting is this picture of her with the insulin. So that is the 3D model that she built.
She's looking at it with real adoration, and rightly so. She worked hard for that.
Look how complex it is. That's one molecule. That's mad, isn't it?
The idea of having to turn it and turn it and photograph it and turn it and turn it and photograph it and turn it and turn it, that is extraordinary. Like the patience that it must have taken.
It looks like loads of fidget spinners, like added together, all different colours representing different things. You know, it looks kind of like that. And it's about, I don't know, a foot tall. If those are the size of fidget spinners, that just shows how big it is and how complex it is as well.
And what a difference to our world, you know?
Well, this is the thing. So, this discovery is absolutely key for diabetes medication today. That, along with she'd already done a life saving drug with penicillin, you know what I mean? She has helped so many people and has embedded in so many lives. But, like I said, doesn't get the credit because you think penicillin, you think Alexander Fleming, you don't think about the woman who actually made it accessible to so many people. Dorothy continued working on insulin until 1988, locating its atoms with more and more precision, so to make it as good as possible. But because she had these other roles in her life as well, they also contributed so much towards her life. She was actually Chancellor of the University of Bristol. I know, from 1970. So she did like giving out certificates and things like that as well, which is very sweet. So she was very integrated in academia. She also, on the side, we haven't really spoken much about her private life, but basically her husband Thomas, I think they were very akin. He was an archaeologist as well, so very much like her father. They had 3 children and I think 3 grandchildren as well. But she was also, I think I mentioned at the start, she was all about peace and living a life of peace and freedom. And she did that in many different ways. She fought for inclusion of Soviet and Chinese scientists at the International Union of Crystallography, which she helped set up during the Cold War. And she served as president of the Bookwash Conferences of Science and World Affairs. So she was very integrated into making science inclusive, just as well.
Nice.
Just on top of everything, like, why not? She died in July 1994 after a stroke. She was aged 84. In her honour, Royal Society established the prestigious Dorothy Hodgkin Fellowship for early stage researchers. And so even though she did all these amazing drugs, she also expanded this realm of science, which is crystallography, which is still very much alive and happening today. And there's a really lovely quote that I thought we could end on by another crystallographer, because she helped expand this realm of science, a guy called, it could be a guy, it could be a lady, Max Perutz. And I think that just sums up everything we've been trying to get across about Dorothy today.
There was magic about her person. She had no enemies, not even among those whose scientific theories she demolished or whose political views she opposed. It was marvelous to have her drop in on you in your lab, like the spring. Oh!
And that is the story of Dorothy Hodgkin.
What a delight! What an absolute delight.
I know, and I do feel like, obviously, skimmed and botched the science as much as possible, but I do think
you summarized and encapsulated the science. I think you'll find
this reframe. But essentially, I guess what I'm trying to say is she has, in terms of people who have changed history, she did that. She so did that.
I mean, like, not to be really basic about it, but just in terms of how many people who are alive who wouldn't have been alive.
100%. Diabetes, classic.
Yes, and infection being treatable. Incredible, absolutely incredible.
And what an
and it just do that without making anybody mad or like.
Well, as far as I know, I don't know. She could have.
I don't mind making people mad. Secret Reddit account on the forums talking trash. Who knows?
Maybe she left some 1-star reviews. We don't know. We don't know. But from what we can see,
kind of nuts that she could have had email. Like, this is somebody who so
1910 and then 84 years, so that's 1995.
What a lifespan.
Yeah. Yeah. Yeah, and I guess if she was at Cambridge, they probably had email in the 90s, do you think? Because it
Sure.
went commercial before personal, didn't it? So yeah, she probably did
Yep.
have an email address. That's very cool.
And
Yeah.
she created, you know, penicillin in
Life-saving
its
things,
modern
isn't it? Yeah.
form. It's just, wow.
And it's very cute that, yeah, it's just a very wholesome, nice story, isn't it? That she
It
used
was.
those things from childhood and brought them all the way through. And it's
I
a
loved
life
it.
changer. Oh,
Thank you very
fabulous.
much, Vicky.
Thank you so much. And yeah, thank you for listening. We'll catch you later.
Yeah, thank
Bye.
you.